Hey y'all, in this lesson I'm going to show you how to find all of the zeros of a polynomial using the remainder theorem and the factor theorem and synthetic division. We saw in one of my previous videos on graphing polynomials that we couldn't find exactly one of the x-intercepts from glancing at the table of values or looking at the sketch of the graph. And we used the intermediate value theorem to estimate where we thought it might be, but we didn't have an exact solution. Well, that's not really good enough for mathematics. We don't want maybe it's here, maybe it's there. We want an exact solution. And so I'm going to teach you today some different methods as to how to find that solution. I would recommend that if you haven't watched the synthetic division video that you go back and watch that, because we will be using it today to break down our polynomials into smaller polynomials, reduced polynomials, if you will, so that we can find every single x-intercept that we are looking for. We're also going to be using the factor theorem and the remainder theorem. So if you need to go back and brush up on that, you can. But it's all going to tie together in today so that we can find exactly what we're looking for. If you'll remember, when we say that x plus 2 is a factor of a polynomial, then the 0 at that factor can be found by setting it equal to 0 and then subtract 2 on both sides. So the factor at that, the 0 at that factor is -2, which we're going to use for the remainder theorem and for synthetic division. The remainder theorem says that instead of doing synthetic division, if you plug in the x value, if you evaluate the function at a specific x value, if the remainder is 0, then that is a 0 of the function, because essentially what you're doing is you're evaluating the function at an x value, and if you're getting 0 as the y value, then that indicates that it is an x-intercept. If you don't get 0 as a y value, then that's just another point. So I have an example here. We're trying to determine if x minus 2 is a factor of this polynomial. For x minus 2 to be a factor, if it were, then that means 2 would be the 0. 2 would be the x value. So we can evaluate the function at 2, and if we get 0 here, then it is an x-intercept. And you can use your calculator for this. You don't have to do it by hand. 2 squared, that's not squared, minus 7 times 2 plus 10, 0. So as a point, we have the x value and the y value. The point is 2, 0, which means that this is an x-intercept. It crosses the x-axis, which indicates that it is a solution, which indicates that x minus 2 is a factor. X minus 2 is a factor. Not so bad, right? Next example, determine if -3 is a 0 of the polynomial. Now in this case, they've already given us what x is. X is -3. So we'll find g of -3. If you want to pause it and try it on your own and then check back, that's a good way to practice. I'm going to run out of room here, but that's okay. This is a long polynomial. Make sure I wrote it correctly to x to the 5th minus 3x to the 4th minus 9x to the 3rd minus 8x squared plus 2. Then evaluate. At -3, you should have gotten -556, which indicates that the point is -3, -556, and this means it is not an x-intercept, which means that it is not a 0. -3 is not a 0. It's just, it is a point on the graph, but it's not an x-intercept. And I have the calculator pulled up here to the left, and you can see that instead of typing in what I wrote in the first line, I can actually just look at the table of values to figure out what the y value is at that point. So maybe a little bit faster, maybe not. This was kind of a long polynomial, so I wouldn't necessarily call it faster, but you can do that. That is a way. And then the rational zero theorem, this is what's going to help us with that example in my last video on graphing polynomials. This is going to help us find that solution that we couldn't quite see exactly. We knew that it was between two x values, but we didn't know exactly where it was. Well, that indicates that it's probably going to be a fraction. So we can use the rational zero theorem to help us narrow that down. The rational zero theorem says that if you have a polynomial in standard form and you take the, let me put this in standard form, plus 14x squared minus 7x minus 10. If you take the constant over the leading coefficient, they call that P over Q, then you can find the factors of each, 1 times 10, 2 times 5, 1 and 3. And then you're going to write the different combinations of fractions that we have here, 1 over 1, 1 over 3, 2 over 1, 2 over 3, and so on, to find the possible rational roots. Then we can go on and test these possibilities to figure out which one is the rational zero. So when you write out your possibilities, you have to also consider the positive and the negative cases. So for your first possible rational zero, you would have plus or minus 1, and so on. And when you write out your combinations, you would have quite a few different combinations here, and we could just work our way through and test each one, which we'll do in a little bit. So we can do the same thing for the next example, write it in standard form. And then P over Q is the constant over the leading coefficient. Write out your factors, and then set up your possibilities. And then you just you do each combination, 3 over 1. 3 over 3 is just 1, so I don't need to rewrite that. And then 9 over 1. 9 over 3 is just 3, so I don't need to rewrite that. So this one had a few less possibilities, which is much nicer. Now, once you have your possible rational roots, you can start using the remainder theorem and synthetic division to help break down your polynomial. And as you break down your polynomials to smaller and smaller and smaller, then you start to find more and more zeros. Now, if you have like x squared or x to the third, it's a very short process, nice and neat. It's when you have x to the fifth, x to the sixth, seventh, eighth, whatever, that it's really, really big, and you really have to start working your way down to something that's a lot more manageable. Now, remember that if you have not watched the video on synthetic division, I'd recommend that you go back and watch that. This is just kind of a diagram to show how synthetic division works. You set it up with the 0 on the left. You have your coefficients on the top. Bring down that first coefficient, multiply up, add, multiply up, add, and so on. If the remainder is 0, then the factor divides evenly, and it is one of your factors. If the remainder is not 0, then it is not a factor. Long story short, we're going to skip down to an example that I really like down here. We are using the rational root theorem and synthetic division to find all of the zeros of this polynomial. You're going to want to write this in standard form first, which means that you write it in descending order So that's 2x to the fourth, 9x to the third, negative 27x squared, negative 44x plus 60. Goodness. And then your possible rational roots are found by your constant term over your leading coefficient. Now, unfortunately, 60 has a lot of factors, but we can write those out. It's not so bad. 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, 6 times 10, 11, 8, 9, 10. I've looped back around. And we have a very long list. Luckily, 2 is just 1 and 2. So if we were to list out our possible zeros, I am probably going to run out of room here, but we can list them out. Go ahead and pause it and try it and then come back. It really didn't turn out to be so bad because a lot of them reduced to possible rational roots that we already had, but it is a lot, especially when you consider the positive and the negative. So what you're going to do in the next step is you're going to start testing possibilities. And I usually will start with the non-fraction possibilities. And you're just going to start plugging those in, evaluating the function at each of those, and see which one has a remainder of 0. I'm going to start with 1. Oh, sorry, this is g. G of 1. So I'm plugging in 1 everywhere there's an x. And when you evaluate this, I got really lucky on this. It comes out to 0. Thank goodness. So I have found one of the zeros or one of the factors. The factor would be x minus 1, and the 0 would be 1. And I'm going to use that to break down my polynomial. So I'm going to put 1 in my little box. And then I'm going to use the standard form to write out my coefficients in order. And then do synthetic division to find my reduced polynomial, which means I'm going to bring down the 2, multiply up, add, multiply up, add, multiply up, add, multiply up, add. And this is just confirmation that this is a 0 because I got a remainder of 0. And remember that this remainder is the same thing that you're going to get when you plug it into the function. So that all should tie in together. And then my reduced polynomial is now knocked down a power because we divided. And we have 2x to the third plus 11x squared minus 16x minus 60. And this polynomial is still kind of big. So I'm going to use synthetic division again, or sorry, I'm going to use the remainder theorem again to find another 0 that I can use synthetic division on to break it down even further. You can play the game of testing out values. Again, I would recommend starting out with your integer values. I tried -2 and it came out to 0 here. Yay! So now I'm going to use synthetic division on -2 and my reduced polynomial. I will tell you a little life hack. If you type in the original function and you look at the table of values, let's see, and you look at the table, then when you see the table, there's 2 zeros there on the y values. Those were, the first one I actually guessed It was a lucky guess. But for the second one, I looked at the table and I found -2 was one of them. And so I'm going to use -2 in my synthetic division. Whoops. And then my reduced polynomial to set up further. And then do synthetic division again to get a further reduced polynomial. So go ahead and try it and come back. If you tried it on your own, you should have gotten 2, 7, and -30 with a remainder of 0, which makes this reduced polynomial 2x squared plus 7x minus 30. Now at this point, you can continue doing synthetic division, or you can try to factor it, do the quadratic formula, complete the square, anything like that to help you solve this. Usually for me, if I can get it down to a quadratic, then I'm going to go ahead and default to either factoring or the quadratic formula because I just feel like they're a little bit faster. I'm really comfortable with them and I think they're fun. So I'm going to go over here to do that. And I would encourage you to pause it and try that on your own to kind of refresh that skill and then come back. If you factor it, you would get 2x minus 5 times x plus 6, and then add 5, divide by 2, subtract 6. If you did the quadratic formula, you should still end up with the same x solutions because it's the same function. And this right here, we would have had trouble seeing from a table of values, from a calculator. So that's why we kind of have to go through this whole thing to help us find that. We're breaking it down into something understandable, which is a skill you can use throughout your entire life, not just math. You're breaking it down to a simpler problem that you can handle, and then you can find that solution that you can't easily see. So now we have our 4 solutions for this 4th degree polynomial. Isn't that so neat? It's so pretty. So my 4 solutions were -6. I have to go back and remember. -2, 1, and 5 halves. Was it? Yeah, it was positive. 4 solutions for a 4th degree polynomial. Isn't that so nice? So that is how you use the remainder theorem, the factor theorem, synthetic division, and quadratics to find all the solutions. I love polynomials because you get to do all the things. I'm now going to go down to this number 4 for me. And we are using division to find the remaining zeros. So I really like these because it gives you one of the zeros. So we don't have to go through the rational root theorem to help find those and then test them out. It just gives us one, which is so nice. So we can use division to find the rest. If we had the 0 as -1, then that would mean that the factor would be x plus 1. So this is going to help us down here when we're going to write it in factored form. We're going to need this first factor, basically. But as far as finding the remaining factors, I'm going to use synthetic division to help accomplish that. We are using -1 as the 0. And then this is in standard form, so we're using the coefficients. And we're going to do synthetic division. So we'll bring down this -3, multiply, add, multiply, add, multiply, add. So my reduced polynomial, if I started with x to the 3rd, this starts at x squared, -3x squared plus 30x minus 72. And now we have a quadratic. Now that you have a quadratic, you can use a quadratic formula or factoring to solve for the remaining x-intercepts or the remaining factors. So go ahead and try it and come back. I chose personally to factor this one. If you did the quadratic formula, that's totally fine. You'll get the same answer. If you're going to factor, it does have a greatest common factor of -3. So you're going to have to pull that out first. When you pull that out, you're left with x squared minus 10x plus 24. So you're looking for factors of 24 that add to -10. That's -6 and -4. Use the zero product property to split up your factors, solve each one, and you get 6 and 4. Now, I am going through that quickly because I have already taught it in previous videos. If you're struggling with anything here, I would recommend going back and maybe watching some of those. But now, for a third degree polynomial, we have 1, 2, 3 solutions. Wasn't that so nice? I thought it was extra nice that we were given the first one. I just love that. So my zeros are -1, 4, and 6. And then if we were going to write this in factored form, this was, they didn't tell us, so we'll call this f of x. And we're going to be using all of our factors, including the -3 right here. It is a constant factor. It doesn't have a variable with it, but it is part of our polynomial because it is our leading coefficient. So as part of our leading coefficient, it does still need to be in our final answer. My factors are these that I found times the first one that I found. There should be 3 because it is x to the third. So we have -3 as the leading coefficient, and then x plus 1, x minus 6, x minus 4. And that's factored form. So we have standard form and we have factored form. And if we were to multiply this out, we would end up with our original polynomial. Isn't that so fun? I just love this. I love how I love how mathematics just all ties together beautifully. Goodness. All right. I think this is the last one we're going to do today. Let me just check. Yep. This is the last one we're going to do today. I would encourage you to pause the video, read this question, pause the video, and try this on your own completely, and then come back and check with me. So hopefully you did this on your own, and when you come back, you should see that if 1 was the 0, then x minus 1 was the factor. And this is really only going to help us down here when we're writing in factored form. If your goal is to just find the zeros, then you don't really have to do this step necessarily. But the x equals 1 is going to help us write that reduced polynomial. So 1 goes in the box of your synthetic division, and then your coefficients go beside it. And when you perform synthetic division, you end up with your reduced polynomial. And since we started with x to the third, our reduced polynomial is down a power. So we have 5x squared plus 17x plus 6. This is factorable. So if you factored, you should have gotten 5x plus 2 times x plus 3. Or if you did the quadratic formula, that's fine too. In either case, you should have gotten -2/5 and -3. So our 3 solutions for this third degree polynomial are 1, -2/5, -2/5, and -3. So -3, -2/5, and 1. And then if we write this in factored form, we'll call this g of x. You might notice that the leading coefficient is 5. And in the previous example, we had that outside in the front. But if you look at one of these factors, it has the 5 in it. So I don't need to write it again, which means that my factors are going to be 5x plus 2, x plus 3, and x minus 1. That's all I have for finding the zeros of polynomials. If you have any questions or need anything, please let me know and I would be happy to help.